shade. I'd ask my friends to come and see. Right up the closest garden with me. I'd like to be under the sea in an octopus's garden in the shade.
All right, good afternoon. How's everybody doing today?
Great!
Excellent, excellent. Welcome back to class. Today, the topic of our lesson is control structures, which is lesson 28A. Today is March 30th, which will be the Monday after spring break. So, our learning objectives for today are that by the end of class, you can list the common types of weirs, and that you can evaluate Q, your flow rate, do those calculations for sharp-crested rectangular weirs and triangular sharp-crested weirs. So let's look at weirs. And I'm going to make this extra dark because my producer has told me that that doesn't work out so good. So we're going to look at weirs, and to do that first, we're going to look at a definition of what they are. And essentially, we can define weirs as hydraulic structures that are used to control or flow with a known stage discharge relationship. So if you remember back to our lessons, that would have been 29. We talked about the importance of critical depth. We talked about how important it was to have one depth, so one wide to one discharge. This is how you can make that happen with specific weirs. So let's take a look at the PowerPoint. So the first slide there is hydraulic structures, and they are always used to regulate, measure, and or transport water in open structures. We're looking at flow measuring structures right now, that is weirs, gates and stilling basins or regulation structures, and then discharge structures to get rid of water are culverts. And so what we're looking at to try and create is this beautiful stage discharge relationship, right? This is our famous one from Embudo, from John Wesley Powell, where he picked that spot where it automatically knocked the energy far enough back in that narrow gap in the Rio Grande Gorge to force it through critical depth over a range of flows from pretty much 200 up to like 15,000 CFS. So this is what we're looking at trying to make, a stage discharge relationship that gives us flow depth, one flow depth for one discharge. Okay? And the purpose of these control structures is to measure and control flow, to impound water, and to store energy. So I'm going to put these up on the board as well because they definitely need to be in your notes so that you understand why they are important. So essentially the purpose is to measure and control our flow rate, also to impound water. This is going to be a great example in a video. So this is going to be to increase attenuation, and they can also be used to store energy. I've got a great little video to show you here. And this video actually implies to what I was talking about at the end of lesson 29. I talked about the coronavirus and talked about how to actually decrease that peak. this is essentially what is happening here as well. So if you're storing water, you're going to see an example. The same amount of water is released in each of these videos, and if you can't see this video very well, it is actually posted up on Canvas under lesson 28, so you can look at it on your own if you cannot see this on the screen. The amount of water and sediment that's released is the same for each of these scenarios. And you can see what happens when you insert a couple of weirs in there in terms of storage of that water. So in one scenario, the town there is completely wiped out, and in the other scenario, it keeps the water there. So you're going to see this in slow motion. So that's the scenario where you do not have any attenuation. That's analogous to coronavirus, everybody going out and being everywhere. And this is analogous to having control structures in there. That fits with coronavirus. This is everybody staying home and not going outside, not getting in public places. And you can see how those peaks are greatly reduced. We don't have flooding, and it's literally the exact same scenario with two weirs put in there, and that shows you how they can be used to impound water and increase the attenuation. So that means dropping that peak of flow down even further. So you've got that video, you can take a look at it. I watched it about 6 times this morning because I just can't stop watching it. It's awesome. And next we're going to move on to the types of weirs that are important to us. And we're going to have 2 different categories. We're going to have a sharp-crested category, and we're going to have, for lack of a better term, a not sharp-crested category of weirs. And the weirs that fit into those categories are, for sharp-crested, which is what we're focusing on today in lesson 28A, is rectangular, V-notch, or trapezoidal weirs, or, that's V-notch, make that correction in your notes, is V-notch, or triangular, I got a little ahead of myself, and this one down here is trapezoidal. Those are often called Cipolleti weirs. There's 2 T's in Cipolleti. And then not sharp-crested, those are going to be your broad-crested weirs, which will be the focus of our next lesson, 28B, or OG weirs. You actually know what that is. It's what we use on dams to relieve water if we have too much, and that's generally just a spillway with a nice round broad crest and a really steep slope behind it. So those are the main types that we're going to be looking at. And right, we're engineers, so you're probably wondering, how do we actually even analyze these? And the analysis, the beauty of it is, you already know how to do this. Very simple. You've got your energy equation, right? You've mastered that, and we couple that with QVA, or continuity, and that's basically it. So these weird equations that we're going to be looking at here are some of the simplest equations that we'll be looking at throughout this semester. So let me give you a couple of examples. So on the PowerPoint here, you can see that that's a trapezoidal sharp-crested weir, that's a Cipolleti weir. These are more rectangular sharp-crested weirs made out of concrete. Then we have V-notch weirs. Those are usually a steel plate. And you've probably seen this before, right? Most of you are either civil or environmental engineering majors and have probably done one of the field trips to the water treatment or wastewater treatment plant. V-notch weirs are really, really precise at measuring flow, and they're often used in water treatment plants, wastewater treatment plants, and they're actually used quite a bit in manufacturing. And you'll see why those are used when we look at the equations for why they are important. They're really, really good at measuring precise flow rates because of the way that the head over the crest of the weir relates to that. So here's another example of some Cipolletti weirs. We've got an example of a broad crested weir being built, and I showed you some of those in class, some of the ones that I built. Looking at another broad crested weir, and then we've got another broad crested weir showing the subcritical depth upstream, the critical depth over the crest of the weir here, and that's where the measuring structure is in that stilling well, and then your supercritical depth linked to a hydraulic jump below there. And then this is the type of broad crested weirs that I built for my research back when I was doing my PhD in New Mexico. You've seen these all before. So some of the other sharp crested ones that can be used are actually some of these gates. This is called a Langman gate, and it's analogous to a hinge on a door. It opens up like that, and then it closes, and this actually acts as a really narrow, sharp crest, and water spills over it to do very, very precise flow measurement. And here's an example of one of those in action. You can see that water spilling over the crest of that weir. This is the Angostura Dam in New Mexico, and then this is the San Acacia Dam in New Mexico, looking at that same type of thing. So for this specific one, this was a precise measurement that had to be made for water concerns for the endangered Rio Grande silver minnow. And that gives you an idea as to what we're looking at with these weirs and what they do. So, because even though we're remote, we still have to have some demos. We've got some demos to show you. So the first one that I want to show you is a sharp crested rectangular weir. These are 3D printed, but that gives you an idea of what that looks like. And in reality, the water will be flowing like this, and it'll spill right over the crest. That's what that would look like with a sharp crested rectangular weir. Then the next one is a V-notch or trapezoidal weir. And what that would look like is something like that. You get a good idea, water's flowing through it, pours through that notch, and these are usually 60 or 90 degrees. We'll look at that in the equation. Then we've got a Cipolletti trapezoidal weir. You get an idea what that looks like. Same type of thing. This is the direction of flow. Flow will flow over that weir. And then this is an example of a broad crested weir in your standard irrigation canal with a 45-degree slope and a 1-foot base essentially. But that flow would be going like this, and this would match those pictures you saw in the PowerPoint of that little mini speed bump in there. And that's a broad crested weir, which we'll be focusing on during the next lesson. All right, so let's dive right into it, right? I'm sure you want to know how to actually calculate this, because that's our whole point. That's our learning objective. That's what we're trying to get today. So let's take a look at how to actually do calculations for a sharp crested weir. I'll make that really dark if I can. Big bold letters, sharp crested. So for a sharp crested weir, we're going to look at a case where the weir is rectangular. You're going to have to know a term here, and that means we're looking at another definition. So we're going to look at a suppressed weir, and what that means is there's no contraction, and essentially that means it spans the entire channel width, which is usually defined as B. Now let's draw this out. Get a good idea. So if this is your channel bed, and you have a sharp crested weir in there that looks like that, you're going to have your flow rate going over the top of it. You're going to have this great overfall, looks something like that. And you're going to have two variables that are important. H sub W, which is the height of the weir. And the next one is just going to be H, which is the head over the crest of the weir. I'm actually going to make sure I put this in black. Those are the two main drivers. So the main driver for the entire process is this H. It's head over the crest of that weir. And this is generally measured 1.5 channel widths upstream to avoid any turbulence that's being caused by that. That's usually where you set your hobo pressure transducers to measure that. I guess we should probably put that that's water, just in case. So, then we've got that. So let's look at our equation for how to do this. And for this, going into the page, B is going to be our crest width, which in this case is essentially our channel width. What does our equation look like for this? It's going to be Q is equal to CD 2/3 square root of G times your channel width raised to the H over the 3/2. So Q is our flow rate. CD is our discharge coefficient. CD, that's our discharge coefficient. And that's approximately 0.62. I forgot something here. This is actually supposed to be 2G. So that's gravity. B is our channel width, and H is our head of water over the weir crest, and that's usually measured in feet or millimeters. You can find this in your textbook. This is equation 7.67. It looks like it's on page 284. Another equation that I'm going to put up here real quick is, so this equation here is for all units. So I almost always just use this exclusively. You can put in cubic meters per second. You can put it in cubic feet per second, and it works. You had a question, Kevin.
Is the discharge coefficient universal, or is it specific to each weir?
The discharge coefficient is going to be specific to different weirs, and so we'll get to see that when we get the other equations up on the board. But those are different on each weirs, and I'll usually be giving those to you. So depending on how you build them, how you put them out there, each one's going to have their own specific discharge coefficient. So if we're looking at US units, we're actually going to have an equation that we can use. I don't necessarily recommend it, but I'm going to put it in here because oftentimes this is what you're going to see on the FE, and in your worksheet you're going to see this as well because I've got it on there so you do it at least one time. So this is CW, and as you can see, this coefficient of the weir includes gravity CD, the 2/3, and basically gets rid of all those portions, but this is for US units only. So the weir coefficient, if you're using what you might see on the FE, that weir coefficient is going to be 3.33. I'm going to put big notes here. This whole thing is for US units only, so don't get that confused. I can tell you right now, when you're celebrating, there is going to be a question on there where I might throw in cubic meters per second in meters for weir dimensions. I'm just warning you. So don't get too comfortable using this equation because it might come back and bite you in the butt. Now, this equation, if you're looking for it, this is 7.73 on page 285. And generally, what we can do is, since our analysis for these is based on the energy equation, one huge assumption we have to make is that we neglect our approach velocity And that's usually an okay assumption. You will have a problem in your homework where I said that you cannot neglect the approach velocity. So for any of these equations, if you want to account for approach velocity, instead of h to the 3/2, you basically have to do, you do h plus, this is v sub a, which is v approach, over 2g raised to the 3/2. So in either one of these equations, if you want to account for approach velocity, you just take this piece and plug it into there. Or you take this piece and plug it into right here. And that way, you can actually do calculations to check and make sure that you're accounting for approach velocity and that it is negligible. So if you do this equation, you just account for h, great. If you want to make sure that your approach velocity v sub a is negligible, just come back, put va squared over 2g into here. Usually, if you've got a well-designed irrigation canal, right, we talked about this last time, what is your general velocity?
Less than 4 CFS?
Less than 4 feet per second? Yes, probably. What do you think? What would you do? Baptiste, what would you do?
Float method.
Float method, right? You get it, but do you remember what our velocity was? Like for a well-designed irrigation canal? I know, it was the last lecture of the class for real. It was Friday. It was Friday the 13th. It was coronavirus outbreak. Right, we talked about it.
All I remember is less than 4 CFS.
Less than 4, yeah, less than 4. It was less than 4 feet per second. But generally, you're trying to design it to be 1 foot a second.
1 foot.
Right, so 1 foot a second will still transport enough sediment through your canal, and it will not erode the banks of the canal. So you can imagine, if you have 1 foot a second squared, so that's 1, divided by 64.4, that's essentially nothing. And so in most cases, that works out just fine. So thanks, Baptiste, that was great. So with that, right, we've got our setup for most of the cases when we're looking at weirs. So everybody got this? Everybody's got this in their notes?
Yeah.
Okay, I don't hear any clicking. I think we're set. Perfect. Now we're going to move on to the case that I just actually showed you. In that case that I showed you, right, I'm going to run over here and show you this 3D printed weir again. Now, what's the problem? What's different from what I had up on the board in this? Does this span the entire channel? No, it does not span the entire channel, right? So this is often the case where you see this little pinch in on the sides where the channel is actually contracted. So this is no longer a suppressed weir. This is what we call a contracted weir. And in most cases, we're going to be dealing with contracted weirs. So we need to augment our equation to account for that. And I'm going to show you how to do that here right quickly. So if our sharp-crested weir is contracted, how do we account for that? All we have to do to make this work is we're going to replace B, right, which is our, what is it? What is it, Zach?
Was it the, no, it's not the depth. What was it? The width?
Yes, the channel width,
Yeah.
right? So we're going to replace B, our channel width with B prime. I'm going to show you how to calculate that. So there are two different cases where we can have weirs, right? So this is like the one I showed you where it's contracted from both sides. And then there's another case where we can have our weir contracted from one side only. Okay?
Can you also draw this same profile but of the last weir? That you're not.
Oh. Yeah, hold on. I gotta get these first to be the same. Getting so excited I forgot. You gotta draw these to match. Okay? And what was the other one?
And then the last one that we just did the calculation
You like
for.
it flowing through there?
Yeah, but it did because you drew it at the side profile, but this is the straight on.
Yeah, this is the straight on profile. So what this would look like, obviously the two are going to be a little different, but you would have something like, so this would be that weir, but you'd have that notch in there like that. And you'd have water essentially pouring through like that and then going like that. So this would be what that would look like from the other side. So if these are contracted, okay, your general channel width, right, is going to be B, but you have to replace that with B prime for this case. And so there are two different conditions here. So if you actually have water in here, let's take a look at what's happening. And for those movie buffs out there, this is going to be awesome. You're going to love this. So this is the case where n equals 2. This is the case where n equals 1. And what you're looking at here, this is your head-on view. If you want to do let's do a plan view. Probably wondering like, what is Dr. Kinsley talking about? He's talking about movies? So this is your plan view for this one. And this is your plan view for this one, right? What's the water doing? Why do we have to replace B with B prime? Look what's happening. Water comes in here. We'll do something like that. Come around like this. And this one's going to do something similar, right? So what will happen, and this is why I was referring to you movie buffs out there. Who's seen Zoolander?
Me.
You've seen Zoolander? Excellent, Ethan. I'm not going to specify which Ethan you are, but what can't Zoolander do?
Oh God. Breathe good.
Breathe good? That's not quite it. It has to do with the runway. What can't he do?
Oh, I don't remember.
I think he can't turn left.
You can't turn left, okay?
Right? He's not an ambi-turner, as they say
God,
in the movie, right?
okay.
So, what can't water do? So water's a lot like Zoolander. I'm going to put this in big red letters at the bottom. Water can't turn left, but water can't turn 90 degrees, right? Water's really similar to a car. You think about driving along the roads. Can your car do a straight, like 90-degree bend path? No, it's always got a curve to it. So that's why all our intersections are designed the same way, right? You've got some specific curve based on the speed of your vehicle. The water's the exact same way. So what actually happens is this water using this entire width? It's not. The only width it's using is probably this width right here. And in this case, it's probably only using this little width right here. And so we've got to actually account for what we're looking at. So, for our correction equation is going to look like this. Our B prime is going to be B. Now, is that going to be the width of the entire channel, or is that going to be the width of the weir?
It's probably the width of the weir.
Yeah, it's the width of the weir. So we're not going to be using this B. We're going to be getting that B from here, and from here. So this is that V. It's the actual width of the weir opening, okay? Minus 0.1 times N times H, where H is the head over the weir crest, N is just how many contractions you have based on the type of weir that you're dealing with. So N equals 1 is a contraction against the sidewall. N equals 2 is the contraction not against the sidewall. And B in this equation here is, I'm just going to define this as the weir opening width so that you don't get confused as to what you're doing. Okay. Any questions, concerns? All making sense? All right. So let's move on. That gives us sharp crested weirs, and so now you have the tools to do everything for sharp crested weirs. When you're doing your weir equation, think back, this B prime, that's what goes into B, into the equation that I had right here, and then the equation I had right here. That's the actual width of opening that the water sees, that it can flow down to. All right, and the last one that we're going to look at is triangular or V-notch weirs. And if I do a head-on view of a triangular V-notch weir, that's essentially what we're looking at. You're going to have some level of water in there, and then your head over the weir crest is going to be to the notch. This notch generally has an angle which is going to be 60 or 90. Usually how they're made. And the equation for this is really easy. This one doesn't have any weird contractions or anything. They're always just this equation, which is going to be 8 over 15 CD times the square root of 2G times the tangent of theta over 2 times H raised to the 5 halves. And this is equation 7.84 in your textbook. It's on page 289. And you get your CD for these from figure 7.20, and that's also on page 289. So generally, these are, you can often get these. Traditionally, a standard CD for this is usually 0.58, somewhere in that range, or a little bit less efficient in terms of maintaining energy because it is a more drastic contraction. But you can get those from that figure on page 289 in terms of what those contractions look like. Now, the last thing I want to talk about here for this lesson is, you see this difference, how that H is 5 halves in this one, and before it was 3 halves? So that means if you change the flow at all for this, that's going to change the H substantially more than it does for sharp crested rectangular weirs. So that's why for different flow measurements, if you've got a staff gauge, any tiny change in flow is going to have a much higher H for a triangular V-notch weir, and that's why they're used in precise measurement applications like in manufacturing, like if you're manufacturing paint or chemicals or anything of that nature, they're often used for this. Brewery has a ton of these, by the way. So, all right, so now, please do worksheet 28A. That worksheet is posted up on Canvas. You've also got a hard copy from the last couple of days of class. We've got the solution for that posted. And if you've got any questions, please feel free to email myself or Jake, and we'll be answering your questions. Sorry that is not quite as entertaining as usual, but yeah, don't really get to ask too many questions. Yes!
So
wait, I gotta come up with a name first. I'm not ready. All right, Victoria, you have a question?
yeah, so the triangular V-notch, that
Yeah.
equation, is that for any units as
Yes,
well?
yes, that is a great clarification. So I'm just gonna put here that this is good for all units. So it's similar to the first sharp crested weir equation I put up there. So I would try to stay away from the US unit ones. I only have it on there because that's how the FE does it. They always ask the sharp crested weir equation with the CD of 3.33. All right, any other questions? All right, let's check into our learning objectives. How are we doing? So after completing the worksheet, 28A, do you think you can? First off, list the common types of weirs.
Yeah!
Yeah, can you evaluate Q for a sharp crested rectangular weir?
Oh yeah.
Oh yeah, definitely. And can you do the same for a triangular sharp crested weir?
Most definitely.
I bet. So worksheet 28A has all of those types of weirs on there. Please make sure to go through and do that worksheet. It will definitely be on the next celebration. So it would be wise of you to make sure that you know how to do that entire worksheet. Have yourselves a wonderful rest of the day, and we'll see you back here on Wednesday.